Good morning, everybody. I'm glad to introduce Lorenzo Marra for this seminar. Lorenzo took his PhD in Roma 3 and working on modelization of X-ray emission of black hole X-ray binaries, focusing in particular on X-ray polarization, working within the IAPS collaboration. And now he's in Padua. He has a postdoc in Padua, where he continues to working on modelization of black hole X-ray binaries, particularly working in black hole X-ray binaries in soft state, if I remember well. And he started to work. He's starting to work also with magnetars. Seminar will be on black hole mostly on black hole, if I remember. Yes. And some before I let the floor to Lorenzo, I would say to the group that the questions have to be done after the end of the seminar. In particular, for people connected online, please write your questions in the chat because the microphone doesn't work well. And unfortunately, and so I can now let the floor to Lorenzo.
Thank you. So, good morning, everyone. Thanks to Fiamma for the introduction, and also thanks to the organizer for giving me the opportunity to be here today and present this seminar. So, the topic that I would like to present to you are the polarization properties of the X-ray emission coming from stellar mass black hole and substate, focusing on both the theory and the first observation obtained by IAPS. So I would like to start with a quick introduction. Stellar mass black holes are objects that are found usually in our galaxy in binary systems known as X-ray binaries, which are composed by a normal star and a compact object that can be either a neutron star or, such as in our case, a black hole. So these objects are among the brightest X-ray sources in our galaxies, and the actual source of the X-ray emission is this axisymmetric structure that forms around the compact object that is known as the accretion disk, that is basically composed of the material that is drawn from the normal star and accreted onto the central object. Because of the viscosity between adjacent layers, adjacent rings of the accretion disk, the temperature of the inner regions of these structures can reach very large temperatures, up to 10 to the 7, 10 to 6 Kelvin. And thus, this temperature allows this structure to emit radiation in the X-ray band. So traditionally, these sources have been classified in two categories depending on the mass of the donor, the companion star. We can either have a low mass X-ray binary where the accretion is fueled by a Roche lobe overflow. So basically, during its evolution, the companion star expands, filling its Roche lobe. And at this point, basically, some material from the companion star can pass from the inner Lagrangian point and be accreted on the central black hole via the accretion disk. The other case is the high mass X-ray binary case, where instead the companion star is a massive star, and in this case, the accretion is mostly fueled by the winds emitted, so this material emitted from the surface of the companion star. So black hole binaries are usually transit objects. There are some exceptions, but most of them are usually found in a very low luminosity state for most of the time, a quiescent state. And so they are not observable unless they go into outbursts. And these outbursts are characterized by a large increase by several order of magnitude of the luminosity of the object, and can last from a few days up to several months. So these sources are typically highly variable. Their X-ray spectra is usually characterized by having 3 different components of different, which give different contribution depending on the source and the time of observation of the source. So we have this thermal emission coming from the accretion disk that is usually modeled in the standard Shapiro-Swinnerton model of a geometrically thin and optically thick disk. Then we have this continuization component that is instead produced by compound scattering of the seed emission coming from the accretion disk. And this is believed to be produced in a region known as X-ray corona, where basically we have an optical thin and very hot plasma. And finally, we have this third component that is only observed in some sources, that is the so-called reflection component, that is produced by photons that are either emitted from the corona or from the accretion disk itself, as I will later discuss. And this component, these photons are basically forced to return to the disk surface, where they are reflected by the disk atmosphere before eventually reaching the observer at infinity. And if this medium is not completely ionized, what can happen is that some of these incident radiation may be absorbed by the disk atmosphere and later re-emitted as fluorescent lines, the most important of which is the iron chaos line that you can see here in the blue spectra of an archival observation of Sinus X3. So we have these three components. These sources, as I said, are highly variable, and in fact, observing two different sources, but even the same source at different time, we can observe very different spectra. And a model to actually unify all the different behaviors of these sources has been proposed almost 20 years ago, actually. And it's based on the fact that if we trace the path of an outbursting source in an hardness intensity diagram, like this one on the left, where we have the hardness, so the ratio between the fluxes in two energy bands, usually an harder band and a lower energy band. On the x-axis, while we plot the intensity of the source during the outburst on the y-axis, we can find that most outbursting sources tend to follow a similar path, that is also known as Q-shaped path. And in this path, two main spectral states have been identified, of course, with all the possible intermediate states between those two. So we have this hard state on the right, in which the X-ray emission is mostly determined by the emission coming from the corona, the quantized component. But the state I will mostly focus on is the soft state, so this one on the left. In this case, the flux is dominated by the emission coming from the accretion disk. And because of this, the accretion disk is expected to extend inwards towards the innermost stable circle orbit, the ISCO around the black hole. So if we find a way to estimate how close to the central object the disk extends, then we can use the well-known relation between the ISCO and the spin of the black hole to find an estimate of the spin of the source. This is something that has been done in the past by several authors. There are actually two main techniques that are well established in the community. The first one is the so-called study of the reflection spectroscopy. So the idea here is that the reflection component, and especially the emission lines that characterize this component, so their profile is modified by several relativistic effects due to the fact that this reflection happens in the inner regions of the disk. And thus, some effects like Doppler shift or gravitational redshift can modify the shape of the line. Here, for example, we have the iron line profile for several values for two values of the black hole spin and three possible inclinations. And basically studying the profile, modeling the profile of these lines and the reflection component as a whole allows for an estimate of the spin and the inclination of the source. This method, as the next ones, actually, of course, depends on several other parameters, such as the mass and the distance of the source. So the same can be said also for the second one, is the continuum fitting. In this case, the idea is to model the continuum emitted from the accretion disk that is, as I mentioned, can be modeled as a multicolor black body, but of course, being emitted in the strong gravitational field of the black hole, This spectra is of course modified by the same effects I mentioned before. And so modeling the continuum of this emission allows for a second way to estimate the spin of the black hole. There are actually two other methods that have been proposed in the past. The first one is the analysis of the so-called quasi-periodic oscillations, QPOs, that are some quasi-periodic variation fluctuation that are observed in some sources. However, this method relies on the observation of 3 simultaneous QPOs in the same source. So this, as far as I'm aware, has been applied just once in this paper, this reference paper, if you're interested. And finally, the fourth one is based on the analysis of the polarization signatures of the disk emission. So I would like to discuss this method in this seminar. And what's the idea here? So the accretion disk emission is expected to be polarized because of the scattering processes occurring before the photons leave the disk atmosphere. And because of the axisymmetric structure of the accretion disk, the polarization vector of the emerging radiation is expected to be either parallel or perpendicular to the symmetry axis. The polarization degree of this emission is usually modeled in literature using the computation that have been done by independently, actually, by Chandrasekhar and Sobolev a few years apart. And those basically assume that the disk atmosphere, they basically computed the angular distribution and the polarization fraction for the radiation that emerges from a plane parallel pure electron scattering atmosphere with infinite optical depth. So considering this model basically means assuming that this medium is completely ionized and that the only interaction between the disk atmosphere and the radiation is through Thomson scattering processes. So what we expect to observe is shown here in this plot on the right. Basically, if you observe basically the polarization degree is expected to not depend on the energy of the photon, but only on the inclination between the line of sight and the disk symmetry axis. So if we observe a source phase on with a 0 degree inclination angle, then we expect to observe a symmetric structure, and thus the polarization degree is expected to be 0. As we increase this inclination angle, we expect the polarization degree to increase up to a maximum of 11.7%. However, those are not the only effects affecting the observed polarization properties of these sources. As was first pointed out by Stafford Connors in the late 70s, there are important general relativity effects, such as gravitational lensing and the gravitational redshift, that influence the polarization observable as observed at infinity. Here in this plot, we have the flux on the left, the polarization degree in the middle column, and polarization angle on the right for 2 possible values of the spin of the black hole, assuming a fixed inclination. And as you can see, the total emission that here is plotted with solid lines is actually composed by 2 different components. The first one, the direct radiation, is composed by photons that here is the one shown with dotted lines here. This is composed by photons that directly reach the observer after leaving the disk atmosphere. But we have a second component that is produced basically by gravitational lensing. That is this returning radiation component that is shown with dashed lines. And this component is produced by the photons that are forced, whose trajectory is bent by the strong gravity. And those photons are basically forced to come back to the disk after the emission and re-interact once again with the disk medium before eventually reaching the observer. And because of this last interaction, this component is expected to have a very large polarization degree compared to the direct emission, and also to be polarized perpendicularly to the direct emission. So basically what we expect is that when at higher energies the radiation component becomes dominant, we expect to observe a transition from the direct radiation regime to the returning radiation regime, and thus to observe a 90-degree swing in the polarization angle, and at the same energy, a minimum in the polarization degree. However, this is actually not the only effect influencing the polarization observables as seen by an observer at infinity. There is another one that is the so-called rotation of the polarization plane. So in this case, what happens is that photons emitted in the strong gravitational field of the black hole are forced to follow the null geodesics in the curved space-time. And their polarization vector is parallelly transported along the geodesics. So what happens is that when we sum up all the photons contribution at infinity, since the polarization vector is rotated during its propagation along the null geodesics, basically summing up all the contribution, we observe a net depolarization of the emission that you can see, for example, here in the direct radiation contribution. So both those effects are expected to be stronger for photons emitted in the inner region closer to the black hole. And since the location of the innermost stable circular orbit depends on the spin of the black hole, the influence of those effects is expected to be stronger for black holes with larger spin. So basically the energy at which we have this 90-degree rotation of the polarization angle and the minimum of the polarization degree can be used as a way to estimate the spin of the black hole. So this is something that was never possible to do in the past. That's because IAPS, launched in December 2021, is the first instrument that is able to detect the energy dependence of the polarization degree in the 2 to 8 kV band. So for the time being, there are at the moment almost a little more than 80 stellar-mass black holes that are known in our galaxy. Most of them are transient, just a few of them are persistent sources. And in its first 2.5 years of operation, IAPS has observed 10 of these sources. 9 of them are point-like. The 10th is the eastern lobe of the black hole candidate SS23 that I won't discuss here in detail. So if you're interested, that's the reference paper. So regarding the other nine sources, those are all the observation. Of course, I won't discuss all of them. But as you can see, basically all of them have been observed at least once in substate. However, the application of the technique I just described, the estimate of the spin of the black hole has been possible only in 3 of these sources, Genus X1, LMC3, and for you 1957. I would like to quickly describe these observations to you, going in chronological order. The first one to be observed was for you 1957, which was observed in May of last year. This is a persistent source, which is quite peculiar because it never went into quiescence. So basically, it's always active. And because of this, actually, we have very limited information on its mass, distance, and inclination. We have some estimates from the analysis of the X-ray emission. So we expect this source to have a large spin and large inclination. Regarding the polarization observation, the polarization degree was observed to be around 2%. With the polarization degree showing an increase in energy going from around 1.2% at 2 kV up to 3.5% at around from 4.3 to 6 kV, while the polarization angle remained constant with energy. And this observation is actually consistent with the standardist prediction. But we have to assume that returning radiation has a substantial contribution in determining the spectral and polarization properties of this source. That's in fact a prediction from the standard model for 3 possible values of the albedo, which is basically the amount of returning radiation that is reflected towards the observer, meaning that with albedo 0, we don't have returning radiation. All the incident radiation is absorbed. While with the albedo 1, all the incident radiation is later reflected towards the observer. And as you can see, in order to achieve an increase in polarization degree with energy, we need a large value of the albedo. The best fit value was actually 0.7. And since the returning radiation contribution depends on the spin of the black hole, because we need the ISCO to be closer to the central object in order to have a substantial contribution from this component. we were able to obtain a lower limit, quite loose, but still a lower limit on both the spin and the inclination of the source. A similar situation was found in the substate observation of X1. In this case, we have a very well-known source. It's actually the brightest amongst massive star, persistent black hole source in the galaxy. It's a source that is typically observed in hard state, but also in a soft intermediate state where it's not a pure, let's say, substate. We still have a non-negligible contribution from a comptoise component. It was actually also observed in hard state, but I won't discuss this here. Regarding the soft state observation, the properties of the source were observed to be quite similar to the one I just described for you 1957. In fact, the polarization degree was found to be quite similar, with also a similar increase with energy, while the polarization angle remained constant. Thus, a possible explanation for this observation is quite similar to the one for the previous source. The polarization is consistent with the standard disk scenario, and also in this case, as for the previous source, the spin estimated from the parametric analysis is in agreement with the estimate from the spectral analysis. Finally, the third one is a little different, is LMC-X3, that is another persistent source, actually. The mass and the inclination of the source are known as well. But the difference is that in this case, the spectral analysis suggests the spin of this source to be quite low, so quite a different situation than the previous ones. And in fact, the observation, when being similar, showed a slightly larger polarization degree of around 3.2%, which resulted to be basically constant below 5 kb, and with only with an increase above 5 kb, which is only statistically significant at the 1 sigma confidence level. So also in this case, the standard model, the standard disk prediction is in agreement with the data. But in this case, because of the large polarization degree observed at low energies, around 3%, we basically have to assume that the returning radiation contribution is not so important because it's not depolarizing the emission at low energy. And because of this, basically, we need the spin of the black hole to be quite low in order to explain this polarimetric data. So once again, the prediction from the polarimetric analysis is in agreement with the spectral analysis. So what about the other sources? Actually, for four of them, the polarization was observed to be too low to be detected. And in these cases, two of these sources are expected or estimated to have a moderately low inclination. That's the case for M61 and GX339-4. So the standard model predicts actually a low polarization degree in this case. So the observations are still in agreement with the standard model prediction. In the other two cases, the two Swift sources, those are two sources that have been discovered last year, actually. And thus, we don't have any constraint on the inclination of these sources. So from this, we can just assume that the inclination of this source is not, those are not highly inclined sources, let's say. So we remain with just two remaining sources, which are the most peculiar one. Those are Genius X3 and 4U1630. Once again, I won't discuss in detail Genius X3 because that's quite a different situation than the standard soft state sources. In fact, as you can see, the polarization degree is way larger than in the previous one. We observed the polarization degree as large as 20%. And this high polarization degree, as well as the fact that the spectra of this source is usually modeled with a reflection component, a dominant reflection component, suggests that we are not actually observing the primary emission coming from the inner regions of the disk, but this is actually obscured by an outflow. And so what we are observing is actually the radiation that is scattered on the inner surface of an outflow with a narrow funnel. But once again, if you're interested in this source, there are this reference paper and many more in preparation on this. And so we are left with 4U1613. That is probably the most enigmatic source that was the most enigmatic stellar mass black hole that was observed by IAPS. And this source is actually a transit source. It goes into outbursts every 2 to 3 years, and we have some estimate on the mass, the distance, and the inclination. The inclination estimate is due to the fact that their wind signature has been detected in the source, which is basically an outflowing plasma that is expected to be located on top of the accretion disk and is observed in some sources by observing some highly ionized absorption lines in the spectrum. And since the model of this wind emission, one of the 2 main models actually, assumes this wind to have basically an equatorial distribution, the detection of such an outflow suggests the source to have a rather large inclination. But also at the same time, this source was never observed to eclipse because of the companion star passing in front of the X-ray emitting source. And thus we have this range of possible inclinations that are most likely for this object. So this source was actually observed twice by IAPS. Once in substate because it went into outburst in August of 2022, was observed after the outburst began, and was found in substate, that is the black dots around there in the hardness intensity diagram. Then in March of the following year, it showed a sizable increase of flux and was observed once again. In this case, it was found in a steep power law state where basically the flux was larger, and also there was a much larger contribution from a compactance component. So what about the results of the polarization? In the first observation, the substate observation, first of all, the spectral analysis resulted to be consistent with a large inclination and intermediate spin scenario. And also, wind signatures have been detected in this observation. But the most interesting part is polarization results, because in this case, the polarization degree was found to be around 8.3, so way larger, 8.3%, so way larger than the prediction from the standard model. This was observed with a sizable increase with energy of the polarization degree, going from around 6% up to 12% with energy, while the polarization angle remained basically constant with energy. So before going into the details of the modelization of this source, I would like to quickly describe the SPL state observation. So as I said, the second observation, the source was observed with a larger flux and a larger contribution from the complex component, but there was no wind detection in this case. Despite the change in the spectral properties, the polarization properties were found to be quite similar to the first observation. Actually, there is just a slight decrease in the polarization degree that drops from 8.3 down to 6.7. And but the polarization degree still shows an increase with energy, while the polarization angle remains basically constant. So the similar polarization result in this source suggests that the geometry of the emitting region in the 2 states should be similar. So in this case, a possible explanation for the slightly lower polarization degree is that because we are basically observing the same emitting region, which is transitioning from Thomson scattering dominated regime to a Compton scattering dominated regime. So basically, the temperature of the electron is becoming larger in this second observation. So regarding the possible modelization, actually, there is, for the time being, no scenario that explains this observation or the details of the polarization behavior in this case. The simplest model is to just look at we did for the other sources, so try to explain the observation with the standard disk scenario. So assuming a pure scattering atmosphere, however, as you can see here on the right for the Chandrasekhar prediction, in order to reach the 8.3 level of polarization, we need the source to have a really large inclination, which is something that is not expected given that the lack of eclipses the sources. So, moreover, even if we assume such a large inclination, the polarization degree predicted by this model is not enough when we take into account the depolarization due to general relativity. In fact, we are way too low to explain the observed polarization degree in this case. Another model that was proposed is that the polarization is due to reflection from a distant wave that, as I said, was detected in the source. However, simulation on the polarization degree expected from this reflection suggests that the polarization degree expected in this case should be either constant or decreasing with energy, so very different from the one observed. And also the disappearance of wind in the second observation suggests that this scenario is not able to explain the data. Another scenario that was proposed is that the disk is not geometrically thin. We have a geometrically thick disk where the disk inflates basically. So this expansion, vertical expansion of the disk basically allows a larger fraction of radiation to reflect off a portion of the disk and basically increases the contribution of returning radiation. However, also this model, while it's able to explain the increase with energy of the polarization degree, it does not reach the observed polarization degree that is shown here on the right with this blue band. So once again, this model is not able to explain the data. And one last model that I would like to describe more in depth is that is based on the idea that, as I mentioned, Chandrasekhar prediction assumes that only Thomson scattering occurs within the disk atmosphere. And a model that we have actually been working on since 2021 is, and that is the one that we applied to this data, is based on the idea to also include in the radiative transfer of photons within the disk atmosphere also other effects such as absorption and Compton scattering. And to do this, what we did is to assume to have a surface layer, so basically an atmosphere located on top of the accretion disk. And we modeled this, the ionization structure of this atmosphere with the photoionization code cloudy, and basically the properties of the atmosphere are only determined by the temperature, the density, and the optical depth of this layer. Then we used the ionization structure obtained of the layer obtained in this way to as an input for a Monte Carlo code named Stokes. And this code basically computes the polarized radiative transfer for propagating within the atmosphere. And we assume the seed emission of this code to be an unpolarized black body coming from the inner layers of the disk. This code, this Monte Carlo code includes several processes such as line emission, photoelectric absorption, and Compton down scattering, but for the time being, it does not include Compton up scattering, which, however, we expect to not be dominant in this case, since we are assuming the temperature of the atmosphere to be the same of the temperature of the underlying black body coming from the inner layers of the disk. So these are basically the results we found in two different configurations. We have the flux on the top row and the polarization degree on the bottom row. Actually, two configurations are the one on the left, where we assume that the ionization is only due to the collisions between the medium, the plasma composing the surface layer. So we don't include the photoionization in the computing the ionization structure. While in the other case, we have photoionization, so the disk medium is expected to be much more ionized. And what changes is that while in both cases we observe the polarization angle to always be perpendicular to the normal, to the slab normal. In the case on the left, in the low ionization case, we can observe some strong absorption lines in the spectra. And in correspondence to this absorption line, we observed a steep increase in the polarization degree. And a simple explanation for this is that when we include absorption, we lose the contribution of photons that are emitted at the bottom of the surface layer with a large inclination angle. So basically, the main contribution given to the emerging radiation is given by the photons that are emitted with a small inclination angle, that are the ones that are more likely to suffer only one scattering, and thus we expect those to be polarized perpendicularly to the slab normal. However, this configuration basically produces in the IXP band a decrease in polarization degree behavior. That's because we have this strong depolarization effect at around 6 to 7 kV due to the emission of important fluorescence lines such as the ROK alpha line. The situation is quite different in the high ionization case. In this case, we don't observe many absorption features, so there is just one, that is the iron absorption edge at 9.1 kV. And what changes basically is that while we don't observe this strong increase in polarization degree, because we don't have that much absorption, we still observe this increase at high energy that is likely caused by compound down scattering. So basically the effect is quite similar to the absorption. Compound down scattering effectively removes photons composing the exponential cutoff of the seed black body, and thus working in a similar way, such as the absorption processes that I just described. So it's interesting to observe that this effect is actually able to produce an increasing polarization degree trend with energy. And that's also, this effect can be observed, we expected to observe it also in the 2 to 8 kV band. In fact, if we increase the optical depth of the surface layer, both the absorption process effects and the compound down scattering effects are expected to be much stronger. So the polarization degree is expected to increase. Thus, with a large enough optical depth, we are able to achieve an increase in polarization degree behavior with energy in the IXP band. So what we did is to assume a standard disk model, sample the disk into 30 radial beams. For each beam, compute the polarization properties of the emerging radiation with this setup I just described. And then using it as an input for the ray tracing package KYN, that is a relativistic ray tracing code that basically works with an observer to emitter approach. So basically, once selected the inclination, the code follows all the null geodesics that go from the observer to the emitting point on the disk. And then it uses the flux parameters of the emerging radiation we computed with the Monte Carlo code as the input of the integration all over the disk surface, which takes into account all the different relativistic effects modifying the properties of the emission. So what happens if we apply this model to the 4U1630 data is that we are still not able to reproduce the data actually. We can explain the polarization degree increase with energy, but once again, the predicted polarization degree that's shown here in this middle panel is not enough, it's too low with respect to the observed data. So a possible explanation that was proposed is that that actually works, but it's quite extreme, let's say, is that the observed polarization degree is boosted by assuming that this atmosphere, highly ionized atmosphere, is outflowing towards the observer with a quite large velocity. So we are talking about a relativistic velocity actually. And this actually boosts the observed polarization degree because of relativistic beaming, and allows for a possible explanation of the source. But as I said, there is still no scenario that explains all the possibilities without assuming a very ionized and very fastly outflowing atmosphere. So those are my conclusions. During the first 2.5 years, I actually have observed a large variety of stellar-mass faults, and several sources have been observed in source data. In most cases, this observation gave results consistent with the standard disk prediction. For the first time, it was possible to measure the spin of stellar mass black hole using the X-ray polarimetry, and all three observations gave results consistent with those obtained with the spectroscopical methods. However, there is this peculiar case of 4U1630 with its unexpectedly large polarization degree that is quite difficult to explain in the standard model scenario. So a possible interpretation may reside in a more detailed modeling of the radiation plasma interaction. So thank you very much for your attention.
Thank you, Lorenzo. I'm going to moderate the question. So I'm giving priority to the people in the room, and then if people online can write your question on the chat, I will then read them. So Stefania, there's a question there.
Sorry, I'm not a specialist of the topic, so maybe the question is not very relevant. But first of all, thanks for the seminar. Thank you for this. Source, you said that the distance is at most unknown by a factor of 3. How this affect your modeling? For instance, does the black hole mass depends on your knowledge of the distance? And the size of the accretion disk depends on the distance. So when you say that you model the general relativistic effects with 30 radial beams, the size of each beam depends on how large is the disk. But essentially, you know that since the distance is so.
So with the distance, I mean the distance between us and the source, basically. And this affects the expected shape of the spectra emitted from the thermal disk, but does not affect the size of the accretion disk. That depends mostly on basically only on the mass of the source and on the spin of the source. So in this case, yes, we made some assumption on both the mass and the spin of this source. We assume to have a 10 solar mass. We assume the mass of the black hole to be 10 solar masses, and we assume the spin to be the one obtained from the spectral analysis, so this 0.7. But of course, the sampling and also the properties, the ionization properties of this minimum depends on both the mass and the spin, of course. In this case, we just assumed the parameters that we found from the spectral analysis and from independent estimates.
Okay. Any more questions? Any, and I don't see any online. Paolo.
It's just in always asked questions that is the fact to reconcile what people from timing says and people from spectroscopy polarimetry says. Fact that the internal part of the disk may be how can be reconciled this picture about of black holes, which the internal part can wobble, and then you have this results of spectroscopy.
So basically, one of the main assumptions of the models that is done in basically in all the sources is that the orbital inclination is the same as the inclination of the accretion disk symmetry axis. And that's because we expect it to form from the material from the star and thus to maintain conserve the angular momentum of the unfolding matter. So yeah, one possibility is that it's not like that, and it's actually something that has been proposed. Actually, I have one more slide for this. I think has been proposed in some sources, so that we have a misalignment between these two axes. So basically, that the inner regions of the disk are misaligned with the orbital inclination. And that's actually something that has been proposed in the hard state observation of Chinesics 1, because in this case, the observed polarization degree of 4% was observed to be too large for the orbital inclination of 27 degrees. And thus, to obtain such a large polarization degree, possibility is to have a misalignment of the inner regions of the disk. So, of course, assuming that we have the same inclination is the, let's say, the safest option, but it's not the only possibility. In some cases, misalignment has been proposed and actually helps boosting the polarization degree, of course.
And just Thank you. First of all, thank you for your seminar, very nice. And I have a question about, I don't know if you had the possibility to see a paper that has been published on IAPS, I think 1 month ago by Fascischi, people, that says that it's impossible to explain the polarization degree of 1730 and 1630. And I would know if you had the possibility to read it. I read only the outside, so I don't know.
No, actually, I haven't read it, but
Yeah, the second question. And have you, if it is possible in the spectra observed by produced by IXP until now, did we see the inversion of the angle? Perhaps I should know this, but I don't know.
so there is just in one source, actually, there is a slight indication. The actual 90 degree swing was never observed. The only source where something was observed, but just an indication, let's say, because it's below 1 sigma. Confidence level is in this source where the first beam seems to be misaligned with the other ones. But that's just really an indication that the actual swing was never observed. Yeah. And basically there is a slight misalignment between the first beam, the first energy beam and the polarization angle in the first and in the following ones. And that's something that goes in the direction we want, actually, because it suggests that the swing happens right at 2 kV or slightly below, and thus we are not observing it. But yeah, that's it has very low statistical significance. So
you assume that the inversion is outside the range of the.
It's likely, yeah. The point is that if the black hole spin is too large, then we expect it to be below 2 kV, and yeah, so we never observed it. We would need an intermediate spin source, such as for U1630, but that's, as I said, a very peculiar source.
So I give no, go Paul.
Just something that in your tentative to explain as for U1630 looks and IAPS, I think the polarization angle is always parallel or perpendicular to the normal to the disk.
So it's perpendicular to the normal, to the slab normal, and thus perpendicular to the symmetry axis.
So it's along the disk, basically.
It's along the disk.
Along the disk.
Yeah.
So maybe this is very important to measure radio.
Yes.
There will be great because it will be very different from the other sources.
Yes. Actually, the prediction from this model for the direct, actually also from the standard model from the direct radiation is that the so-called, so the direct radiation has, I can't find the slide, but okay. The direct radiation is expected to have a polarization vector directed perpendicularly to the symmetry axis, while the returning radiation because of the last scattering is expected to have a polarization vector parallel to the symmetry axis. And thus, yes, of course, if we have some indication on the orientation of the source on the plane of the sky, that
because it's in SWAN, A and R state, and soft state, the polarization, if I'm not mistaken, is parallel to the symmetry axis. So
yes.
So this would be the opposite.
Yeah, but in fact, in that case, we expect the main contribution to be given by returning radiation. But we expect it to have the same polarization angle as the hard component. So in that case, it works, let's say.
So that was not a question. So I'm not an expert in polarized emission from this object. In your talk, you presented a lot of results about polarized emission from the disk.
Yes.
I'm wondering what's the expected in polarized emission from the corona, from the jet, from this accreted source.
So what was observed in for the corona is that actually I don't have many slides on this, but okay, I have these. What was observed in sources not in soft state, so where the contribution of the corona is more important, or actually it's the dominant one, is that the polarization is typically directed in the same direction of the radio jet if it was observed, and that's the case for genus X1. In that case, the main takeaway is that since the corona, one of the main objectives, the main goals of XP for that kind of sources was constraining in some way the geometry of the corona, since there are many models that have been proposed by, they can be discriminated by spectral analysis. And studying the polarization because of the fact that the polarization angle of, for example, genus X1 is in the same direction of the radio jet. This seems to suggest that the most likely scenario, the suggested scenario, is the one where we have this corona to be directed basically perpendicularly in the same direction of the disk, so to have a kind of equatorial geometry. And that's because if we assume, basically in this case, if we have the corona to be directed in this horizontal direction, most scattering will happen in this direction. And thus we would expect the polarization vector to be perpendicular to the scattering plane and thus in the vertical direction, which is the one that was observed. So that's an indication. Regarding the comparison between the two states, the high state for the time being has been observed to be slightly more polarized. That's the case, for example, for this Swift source, which was observed to have a 4% polarization degree in the soft state, the high state, and lower polarization degree in the soft state. So, and that's a similar thing that was observed in genus X1. So these two, I think, are the only sources observed in both states and seems to have a lower polarization degree in the soft state.
All this data come from a mission that was invented 20 years ago and proposed 10 years ago. Now, what would you like to have from the next mission of Polarina? More effective area, more
effective area.
more energy, the band, higher energy band, lower energy band.
So
Pointing flexibility.
I think regarding the energy band, that actually depends on the source. I can only speak about black holes and magnetars. And so regarding black holes, it would be nice to observe a little at larger energies, since, for example, we expect to observe these things. This in this model, this polarization degree peak above 10 kb. So it would be nice to increase towards larger energies. For magnetar sources, instead, most of the emission, the core of the emission happens below 2 kb. So that would be a very interesting area to observe. But I think in general, the most interesting thing would be to increase the effective area and thus to be able to observe more sources, so to have better statistics for the data we have observed with XP.
Thank you. So I don't see any question online. So before leaving, I have some curiosity.
Okay.
I'm also not from the field, so it's not exactly. I was very curious in the fact that you said that for the solid state sources, the general model works pretty well, agree, polarization and spectroscopy. But we also mentioned that there are differences in the albedo between the sources that were measured, because there were some that are low albedo and some that are high albedo. Is there something that we can learn from the difference in albedo? And is the albedo produced by the electron plasma, the electron gas that are in the surface of the disk? Why one would expect this difference albedo?
So, yeah, basically the albedo should depend on the properties of the disk atmosphere. So the introduction actually of this albedo parameter was used as a way to modelize the possible absorption of the return radiation that comes back to the disk to parameterize it in a simple way. So it was just, it's actually quite a simple parameter, meaning that 0.3, only the 30% of the incident radiation is re-emitted. So it's used in this model in quite a simple way. But of course, we would expect this parameter to have a physical meaning, and this physical meaning to depend on the properties of the accretion disk, because that's, I think, a more quite a large. We have many possibilities, let's say, because it depends on the possible ionization state of this atmosphere. If it's influenced by the photoionization coming from below, and if what is composition, that is, we actually don't know, and also on the temperature and density of this atmosphere that so also depend on the temperature of disk. The temperature of the disk itself depends on all the parameters of the black hole, so the mass, the spin. And thus, yes, this is a really rough simplification, just put there a simple number. But of course, we expect this parameter to hide something that has a lot of information on the state of the accretion disk itself. So yes, that's quite interesting. Actually, all the sources, I think, can be explained, assuming albedo 1, because so including returning radiation. In fact, if we assume a lower albedo in this case, what happens is that we don't have returning radiation, and thus this upper limit on the spin becomes way larger. If I'm not wrong, it's 0.7 if the albedo is 0. So let's say that some sources can be explained regardless of the albedo value chosen. Some needs returning radiation, so we need a large value of the albedo.
Okay, thank you very much.